Hello, this is Rohit Maurya, and this is the sixth lecture of Unit 4. As we discussed, Unit 4 is about the slope and deflections, and then we go on further to find or analyze the column and struts. So let's just recap a bit about what did we exactly studied. So first we study about the slope and deflection equation, which is we deduce is EI d2y upon dx is equal to m. We first deduce this, and then we find the different type of methods to calculate slope and deflection in different types of beam. As we discussed, double integration method, Eulers method, moment area methods, strain energy method, conjugate beam methods. But due to syllabus where I'm teaching right now is only discussed and focused only in Eulers and moment area method. That's why I'm discuss these two in this video lecture. However, I also included the double integration method also, which is, as you can see, that out of the syllabus, and other two also. But if any of you who are watching this video needs to learn about these other methods like strain energy method and conjugate, I can also make for these two. So further I discussed the double integration method, according to which we indicated the generalized equation two times, and then applying boundary condition gives us the generalized equation, which is EIY is equal to double integration mdx into dx plus c1 x c2. But the fault in this method is to make different equation when the loading is changes in same beam. As you can see that in cantilever beam, when load is here, the boundary condition changes and analysis has been done in a different way, and the load is moved towards middle point or any distance from support, then analysis is changed. So that's why we have introduced as Eulers method, into which we make a generalized equation whether which part or section of the beam has the loads or not. So into which we cut the beam in various sections of as described or as placed according to the load, and take a moment, and this equation becomes or placed, and we again do integrate this equation two times, and we have a slope equation and the deflection equation, and according to the need to solve the problem, we apply the boundary condition and find the value of C1 and C2. Well, I need to make a few more addition to that video, so I again make a video for this particular method to describe more about by taking some examples or solutions and different things. So let's just pause it here and let's move ahead. Then we introduce the moment area method. This is a different approach to find the slope and deflection. Okay, this also we call Morse theorem, into which we deduce the equation by solving this methodology. It will be showing, and the formula we has is shown here. To find the deflection, we have a formula A upon E, where A is the area of a moment diagram, and to find the deflection between 2 points in the deflected elastic curve of the loading beam, we have A x bar upon E, where A is area of a moment diagram, and A x bar is a distance from one point or a base point in the beam to the moment areas center of gravity. Then we start from the column and struts. We find different cases of column and struts by differentiating the different end conditions, and we formulated different formulas in terms of P, where P is known as the Kepling load, and then further we generalize by introducing the Eulers formula, which is shown in here. P is equal to pi square EI upon LE square, where E is the effective length in all four conditions as shown in here, where L is equal to L for both and is hinged, L is equal to 2L, one is fixed, other is free, L is equal to L by 2 for both and is fixed, and L is equal to L by root 2 for one end fixed, other is hinged. Then we find the limitation for Euler's formula, which is calculated for structural steel, having alpha C is equal to 320 MPa and E is equal to 250 GPa, which is the Young's modulus and stress value. And we calculate the value of L upon K, which is also we called as slenderness ratio, and we calculate as the value is 80. Then we can say that this Euler's formula can be applicable for 80 value, or say till 80 value for structural steel. Then move ahead. The next topic that I'm going to be discussed here as the sixth lecture is strut with centric loading, or say the second formula. So here is figure having two hinged supports or joints. As you can see that we have a load applied at this axis, okay, P load, okay, which is little diverted or say eccentrically placed along the strut, strut. So the value, displaced value of, or say the eccentric value is E, small e, which is as denoted as a distance where load is actually applied. So let E be the eccentricity of the applied load as shown in figure. Reflection Y is measured from the line of action. As you can see that the line of action is diverted from the axis of two hinged of a strut. So all the analysis can be done with this line of action of eccentric or centricity of this strut. So we already know the equation, generalized equation is EI here is 2 d2y upon dx2 is equal to what, minus p into y, and we also converted this in this generalized form where alpha square is we already did this, alpha square is p upon ei. We assume that to solve this equation differential. Then to solve further to find the equation for p, we applied some boundary condition with this figure. According first condition we applied as when x is equal to 0, where you can see here if I move this cursor to 0, if this point is as a base of the axis, or you can say the coordination of 0 0, then if x is equal to 0, the value of y is equal to e. You can easily deduce that if the value of x, which is shown in here, okay, and the value of y is here, if we x value put here, then y is equal to obviously e, which is shown here, okay. Then if we put these values in this formula, we easily sin x, which is 0, comes 0, y is equal to 0, then b is equal to e, and when we put x equal to L by 2, when we put x equal to into middle of the beam, okay, then the slope becomes obviously 0, dy upon dx equal to 0. Then we solve this equation by differentiating. If we differentiate this equation, dy upon dx, the sin alpha x become alpha cos alpha x, and cos alpha x become minus alpha sin alpha x, okay, upon 2. So by we put the value x equal to x equal to L by 2 into this formula, and we get the value of a, and then we put a or b value into this, and then we have a final equation of deflection, y for eccentricity. Let's move ahead because we have to find the value of p. The expression shows the deflection is always there with an eccentric load. It is infinite. If we put the value of 10 alpha L upon 2, which is come from here, okay, if we put the value of 10 alpha by 2 is equal to infinity, then we have the value of alpha L by 2 is equal to pi by 2, because we know that 10 has a value of infinity at pi by 2, okay. Then we have alpha L is equal to pi, and we already know the value of alpha from this equation here. Alpha is equal to p upon ei. If we try to find the value of alpha, we have a under root here. Then we put the value here, under root p upon ei into L is equal to pi, and then after solving this we have a final equation of p, which is pi square ei upon L square, which is same equation as we deduced in the first condition, which is called the Eulers formula, okay, which is same as a Kipling load, as you find it in the Eulers formula is known as Kipling load. However, due to additional bending moment which is set up due to deflection, the strut is always failed by compressive stress before the Kipling load. It states that due to the eccentricity, the additional bending moment always there, okay. Then due to this deflection, what always be there due to eccentricity, going to be fail under compressive stress, okay, before this Kipling load achieved. By means is due to eccentricity in the strut, okay, due to eccentricity in the strut, there is a additional bending moment in the beam or strut. Before achieving its crippling loading, it fails before to get there, okay. So how to find this compressive stress? So we need to first find the y max. The formula of y we already achieved here. Here y is equal to e tan alpha L upon 2 sin ax. So where is the value of maximum value of y to get the failure of this strut? Obviously here where maximum deflection occur, which is L by 2. So we put L by 2 in this equation in place of x. Then we have a y max value x equal to L by 2. Then we have y max is equal to e sec alpha upon alpha L upon 2. Okay. Then the maximum bending occurred as p into y max. Obviously the moment is force into distance, and what force is acting on this axis is obviously p. Then what is the maximum deflection, which is y max. Then what is the moment at this point, Kipling point or the failure point, or where the maximum deflection is occurred, is obviously p upon y max. Then we have put the value of y max in here. Then we have a value of bending moment, which is equal to pe sec alpha upon 2, and we know the maximum stress is equal to what, p upon a. But due to we considering the section of the strut, so we have to introduce additional bending moment, which is add here myc upon I. Okay, and how this myc upon I he introduced, we already know that we studied in the previous chapter, or say previous unit, that the bending equation of a section of a beam or a load having a load is by defining the bending equation, which is sigma upon y is equal to m upon I. You already remember that equation, or I put it here, which is sigma. I can't use the notation here. Sigma upon y is equal to m upon I. Okay, this is the equation. So from this equation we can easily find the value of sigma, which is stress, obviously stress, and here is a additional stress. So sigma is equal to my upon I, where y is a critical section. Okay, where y is equal to critical section. Okay, so we put the value of m, bending moment, here, which is p sec alpha L upon 2, and we common out the value of p upon a from these two. Okay, and when we do that, p easily can be take out from these two. But what about a? We don't have a in here in denominator. Okay, so what we do, we just easily make the multiplication above and downward, and the downward value of a can be easily put out, as you can see here, and the value of I upon a, we put the value a in divided by in division of I, we have a value of k, which is already be known as the cylindrical slenderness ratio of a beam. So this formula of sigma x shows the compressive stress that where the strut going to be fail before the crippling load, as we reduce here. This formula is known as the Second's formula for eccentric load. In this formula, yc is the distance of the extreme compressive fiber and the neutral axis. What the meaning of this? The meaning of this, if we put the cross section of the beam of this strut, then we know that there is a neutral axis. And what is the value of yc? Yc is a critical distance. Yc is a critical distance from neutral axis. Critical distance from neutral axis. Critical distance from neutral axis, where this section has to be having the maximum stress, which is compressive, because we already know that the upper part is always be compressive and downward part is in tension. So this is all about the fourth unit ends here, and we further discussed or we meet in the next unit, fifth unit, which is about the ring, spring, and we also left the torsional part, torsion in beams, so we also discussed this. Okay, thank you.